All right, excellent. If we could, we'll go ahead and call the afternoon to order, and we have our first speaker from NOAA's Geophysical Fluid Dynamics Laboratory, S.J. Lin. S.J., thank you very much. Welcome.
First, I'd like to thank the organizer for giving me this opportunity to finish by echoing.
Hold on one second. You will need this if you want the slide advancer to work.
Yeah, okay.
No, it should work.
All right, maybe I should stay away from this. Thank you for inviting me for this event. I feel it's a great honor and also a great opportunity for me to present some of my work that first and foremost, I would say Bob has a heavy influence. And I'd like to illustrate this diagram here. And although Bob never actually showed this diagram, but I'm pretty sure you have this in mind on how models should be developed. And this is a little bit different from any single organization because we have to go through cycles. For example, when we were both at NASA Gather data simulation office, we certainly do NWP statement. But after that, we have to look at the skill of cost. That's the second thing. And then one of the Bob's interesting things, persistent things, you make a natural run at the highest possible resolution. And natural run by definition is very long run. And to my view and my interpretation, it's actually just like a climate model. And then we identify the persistent long-term systematic bias in the model. And this would in fact bring back to the NWP and lead to an improvement. And by doing the what I call climate simulation, and today you can think about this as well. The longest time scale is the IPCC type, 100 years long simulation. But it also can be included the seasonal to subseasonal prediction. And in my view and Bob's view, I guess it's really the natural run was almost like a subseasonal prediction to me. And I remember that Juan Carlos was working with you. And the first time we run the very high resolution at the time, 25 kilometers fvGCM, we immediately found a huge error. It doesn't take long, actually, 2 weeks to develop. And then it became unbearable. The simulation was totally unreal after 40 days, 30 days range. And that told me a great lesson that actually climate model bias can be, most of the climate model bias, you cannot tell the climate model bias in a few days, no. But in a subseasonal to seasonal run, that's almost, you can see that very clearly. And then actually, once you fix the model's long-term systematic bias, you get a huge improvement, in fact, in the NWP. That's how I will try to illustrate this using the NGTPS example. How was we able to dip ECNW in many cases? And this kind of cycling, it takes, in my career development, this model cycle, you have to change from one organization to another organization, from say NASA to CSDL, and then you get a more climate thinking. But I don't think this is very productive. It takes decades, and for the field to advance, I think it has to take like weeks, or even days to complete a cycle. That's how I see the seamless model to be developed. You have to look at both NWP issue and also climate model issue in one organization in a very rapid development cycle. And Bob certainly do not have this diagram very clearly spelled out, but basically that was the thinking he had at the time. You look at the short-term forecast, look at the structure of the hurricane, you look at the snowstorm obviously, and then look at the long-term statistics of the natural run. That's really what it is. And so I would like to, does that run?
It's on the GoToMeeting, so hold on one second. Let me just. Now try.
So I can do this? Oh, okay. So I had to flashback to the time that before I was born in 1955, and I want to say this, that people make smart decisions at the right era, given the resource they have. For example, you would think that this goal is to notice forecast over 24 hours are possible, and certainly at the time you have to judge the knowledge as well as the computing results. That was a great vision at the time. And the effect, for example, there's a long document that with George Marguerite's own handwriting over the right-hand side. Thinking about seemingly impossible at the time, but you will be laughing at this stage. That the effect of debating about whether to include mountain or not, to include mountain in the model. And also the effect of precipitation can be ignored. Of course, that's the right thing to do at the time. It's not like the Richardson approach that you are too premature. Given the computational power, you do the right thing at the time. And that's also the great lesson I have. That, but going back to today, thinking, I think today we are on the verge of another breakthrough. That we have to think a little bit big. I think those goals are really ambitious at the time. But of course, this is not something our goal. With our capability at this moment. At this moment, I think we have to think a lot bolder than do the similar thing they did before, the kind of frontier in our field. So this basically what I call the every-3 timeline, and in middle, this is the time that Bob hired me as a federal employee. So 1999, it happened like every 10 years. So in 1989, that is almost exactly 30 years ago. So I got my PhD from the GSDL program, and I stood in front of my current office right there. Didn't realize I would be in this office. But that was 30 years ago. My wife took this picture. So 92, I got hired by Ricky Lu to do chemistry transport modeling, and that's how the original finite volume thinking was formed. Because we want to really think differently. And at the time, I also had this great opportunity working with another person. I was supporting scientists at the time, so I had lots of odd jobs. I shift from job to job. But that's one job is I had to modify Eugenia Chalnet's GCM. That's an A-grade first order GCM to a variable resolution GCM. And that gave me the best understanding of the model anywhere you can get. When I was at GFDL, Suki Maharaj said, don't work on the GCM at all. Otherwise, if you want to graduate. So all the students don't work on model. So I started learning model actually when I was, the first GCM I actually started was Eugenia's first order A-grade GCM. And I found that even today, this is the most elegant GCM you can have. Very simple, incredibly simple, but to the point. So you don't have to go to the fancy Arakawa scheme. But I think this, if I want to revitalize this model today, it will probably beat most of the GCM today. You can keep even the OSSE dynamical core in the best. Also, this is hypostatic, but yes, this is simplicity. Simplicity gives you elegance. And then you can actually do very good job. So all the terms are consistently force order accurate. And so I had that kind of great experience. And then certainly start thinking about how to improve some other aspects. For example, most important aspect is really the nonlinear aspect, nonlinear energy cascade. And Arakawa has done his contribution in the 70s. I think those are wonderful breakthrough type contributions. But I think people's mentality has to adjust a little bit. In what we are dealing with, I think Louis gave wonderful example of PV affection in the snowstorm. So incidentally, we actually use PV as a guidance. How well the nonlinear aspect of the model affects PV, instead of just looking at one-dimensional linearized shallow water equation. That was one of the greatest debate I had to have with a lot of people in 90s, and even last year, David Randall and his group also wrote another paper criticizing our grid approach. But I have to say here, although he's not here to defend, that we have to look at not just one single aspect. First of all, judging a model by its grid is worse than judging a book by its cover. Because it's just one single aspect. And then it's how well you do, not just in the linear way. It's really the nonlinear aspect that really make the most difference. So I have to skip because I can talk about this subject for half an hour. But so we after Bob hired me as really my dream job, and I still benefit from that action today. That I become a career civil servant, and we start to think big and for the future. And first action was the development of the what we call the fvGCM and the everyday at the time. Although the fvGCM was already formed earlier with Ricky Lu as the head of the DAO before Bob Etters, but we really pushed far enough. And Bob is the one that provided the final push to become, eventually evolve into today's what we call the fvGCM. At the time that the computing, the other thing I forgot to say is in model development, we had to constantly look out for the future high-performance computing trend. And if you fail to adjust, it will lose your competitiveness. So in that time, we realized that we have to make the model run on the four-side uniform grid on the sphere. And there are so many choices. So my team, under Bob's supervision, we evaluate a lot of different variations. One of them is actually the Akasahara grid with Kevin Ye. You remember Kevin Ye? he later come to OML to work with you. And that was first attempt, but somehow that didn't work out very well. So Akasahara grid was evaluated. I actually also evaluated what is called the Indian grid, the pineapple grid, what's called Fibonacci grid. Oh, actually, we have to be very systematic and pretty much evaluate all the possible grid variations. At least look at this pro and con. And finally, we found something that actually works well with actually the convenience. It's really the Q sphere. The structure of the model is not that far different from the original latitude longitude grid. So Bill Palman and I, we were able to, Bill Palman was here. He's actually the one to get the first prototype of AB3 to work. And I took it from there and gradually improved upon it and making it non-hydrostatic. That's of course the first requirement, because our goal is to be able to use the same modeling system for any type of modeling. Because I remember somebody from a computer industry asked me, what can your model predict? I think about it and say, well, I want to be able to predict everything under the sun. And that was at least the requirement I put on myself. If you cannot be a complete system, if you make certain approximations that violate certain physical principles, that may prevent you from doing thunderstorm prediction. That's what we are actively doing, or prevent the make the ASC coupling not very effective or incorrect. That will prevent you from doing IPCC type climate assessment. And to some of you surprises, I do believe that the design of the dynamic core has a lot to do with the coupling to ocean, because you have to ask, what's driving the ocean? I asked a few people in my group, what do you think what drives the ocean? And that has something to do with how the dynamic core was designed, interestingly, because what drives the ocean is the curve of wind stress, artistic from the dynamic, not the divergence. So the debate between C, D, A, B, C, D, E is really on the divergence component. That's the Arakawa kind of pioneer. And somehow people still use that the guidance of choosing numerical design. I think that was a little bit limited thinking. Look at the ARC coupling. Interestingly, it tells you want to emphasize rotational component, not a diverging component. And what we have done with the PV thinking is really we try to do the best possible in the model to get the best possible nonlinear PV affection. And turn out that most of the climate tests, we always get it work the first time we try. So the IPCC challenge, it took us 3 months at GFL. When I transformed to GFL, it took us 3 months to get the CM 2.1. Previously, there was based on a big finite difference CCM, but it took us 3 months, not much tuning at all. It just worked. So that was, and actually this CCM is still regarded as one of the best, if not best, in AR4. And what we do actually, back to 20 years ago, we helped NASA develop their first version of the finite volume CCM. And some of you probably know it's still their workforce. They couldn't get rid of it. Even they try pretty hard. Because when they do the coupling air to ocean model, other code doesn't work very well. And it has something to do with how the time code is defined, actually. And although it does work to some extent, the performance was the NCAR-CSM, the latest version, with all the fancier new core, still could not beat the one we put in there 20 years ago. And that's a very old version. Some people joke about it, it's FV0. And that's FV1, 2, 3. So this is the NASA FVGCM area. I would say that Bob is the one really pushing and keep pushing and never stop. Even when I left NASA, he sometimes called me and said, "Can you do this?" I was like, "No, I'm afraid I couldn't do it." There's certain things that really beyond, but he's the one keep pushing it. So I say that relentless pursuit for high resolution. We want to say that high resolution is not as simple as turning several parameters in the model and then we get high resolution. There's a consequential changes to the model dynamics and to the physical characterization. And the gravity wave drag is one that changes is so counterintuitive that Von Carlo pointed out to me, because he got the same thing. He said, I found that your model behaves just like the ECM model in the late 90s when they changed to higher resolution. Because the gravity wave drag is just wrong. Because the gravity wave drag was designed for 2-degree model. And you think that increasing resolution, it would resolve gravity wave drag much better. Unfortunately, the lesson I learned today is we are not enough, nowhere near enough to resolve gravity wave. And the model at this kind of even mesoscale was heavily relied on the gravity wave drag characterization. And the gravity wave drag characterization relied on the standard deviation of the terrain. And when you increase the terrain resolution, the standard deviation gets smaller and smaller, so it becomes non-effective at high resolution. So counterintuitive thing to do is, at very high resolution, you want to crank up the gravity wave drag. You thought you were ready to resolve your partial result, but it's not. It tells you you are nowhere near the goal. So at the time, we certainly want to push as high as resolution as we can. And then we have this. There are so many other papers, but I put two representative papers. One is written by Bob here, and the other is Bowen is also here. And this is high resolution, not fvGCM. General promotes on typhoon and hurricane. And this one was pushing really the resolution boundary and toward what's called mesoscale, global mesoscale recovery model. It was close to 10 kilometers. That was very high resolution at the time. So you get an idea. So this would be what Bob wanted to see 20 years ago, but I was only meant to be able to do it 2 years ago. So we work with Spencer on the new generation of GFS, And this is really the high resolution version of the FV3 GLS. And you can see that we sort of passed what is called the Turing test. Alan Turing was the inventor of the modern CPU architecture. And this Turing test, nowadays people call it Turing test, is how your simulation must be able to make it indistinguishable, at least to machine and human eye artificial intelligence. In the artificial intelligence AI area, they call it Turing test. You want to make it indistinguishable. That machine wouldn't be able to tell which one is satellite, which one is model. And the human eye, actually from this picture, I actually don't think you can actually tell if I take out the table label, because I usually fail. I don't know which one is model, which one is satellite. And this is the highest resolution satellite available in the cup, the Japanese Himawari. So high resolution doesn't necessarily guarantee you better result. And but I certainly know this. We have to address the detail. But this is the last year's presentation from ECNWF scientist that I got the slide from him. That this is what we know well before this. So this is their operational model. This is finally mean square error. And ECNWF tried to define their next generation forecast system from their current operational resolution 9 kilometers to graduate to global 1 kilometer. That's now hyper global 1 kilometer. And as you can see, that error actually keep increasing when you increase the horizontal resolution. And this is not totally surprising. Not only their dynamic is not appropriate, their physics is also not appropriate. So we have to see what we can do actually. This is just too graphic here, but it took half of my group's computer education to do this. We tried to carry out a whole year of NWP with global count resolving model. A prototype of maybe next 10 years later weather prediction model. So we run the global 3 kilometer count resolving. We don't have a deep cumulus polarization, so you don't have that cumulus polarization issue. But there's no guarantee you can actually do well on the large scale, 500 millibar high ACC. When you do this plot, it's standard practice. You filter out all the small scale features. Anything smaller than 200 kilometers gets filtered out. So what you are seeing is just large scale. When you increase the horizontal resolution, you are guaranteed to do a better job on the small scale. But this is very difficult to do. So we actually get an equal score with the operational IFS, and it's certainly significantly better than the break. That's the operational GFS. So the NGG GPS in an alternative universe, this would be the title of the paper I want to use. But that would get a lot of people too angry. So this is the title we submit. Advancing Hurricane Prediction is not a next generation forecast system. And we have the ECNWF collaborator here, Linus is from ECNWF. And this paper is well vetted by ECNWF management. So I'm okay to show you this result, but it's not published yet. So we take 2017 hurricane season, and they want us, because we show them some of the things we do better, and they were not too convinced. ECNWF was not too convinced. So they want us to do the whole season. So that's what we did. Every single case, twice daily. That's what ECNWF did. So for Hurricane Irma, we know ECNWF did the best job for Hurricane Irma. And GFS turned out to be the worst. So there are 4 models here: the GFS operational model and the IFS operational model. And there are 2 more models. One is the GFDL model using GFS initial condition. The other is the FVGFS GFDL model using the ECNWF initial condition. And for Irma, they do the best, but when we are using their initial condition, we improve upon the best possible. So you want to ask, what happens when their forecast is the bust? So 2017 is really interesting. For the 2 high-profile hurricanes, they did fantastic job with Irma, and I just show you we did even better. But Hurricane Maria, I think this is a wonderful case because they believe there's something wrong with their data assimilation system. Well, turns out it's not necessary. I think it's both. From this includes all the cases. So all the cases for Maria. So this is the track error from the ECMWF. It's much worse than the GFS. And this is really the outlier for all the global model. And when we use the ECMWF in this condition, that's great. We start out actually similar to ECMWF. That's influenced by initial condition. And then later on, you pull away. And it becomes actually even better than GFS at day 5. And certainly for this case, there's something wrong with their initial condition, but it's not everything. Their model has some problem with the headache. And so the conclusion is, for these two cases, we avoid their bust, and we make their best case even better. And what happened with the whole season statistics? So I think this is a little bit more convincing to the ECM health managers. So this is the statistics of all the cases, from 175 cases to 94 cases. So statistically, this is quite a lot. So when we use their initialization from day 3 to day 5, we have some significant improvement. Although initially, it just followed the ECMWF forecast, as you might expect. The initial condition dominant. And when we use the GFS condition, initial condition, it looks like the GFS forecast for the first 36 hours. But then the model will make a difference, and then it pull apart. So this is an interesting test. Now I want to go back to, before I go back to the mesoscale resolving part. This is also very important to check upon a model fundamental localization. I would say actually this is really, if not 100%, it's 80% determined by the dynamical formulation. It's not really physics. Physics has some role, but it's not the dominant factor. It's really the dynamic and the resolution. And the dynamic certainly and the resolution are kind of hand in hand. So you can see that this is the wind pressure correlation, and ECMWF forecast is like this. And the black are the observations. And when we, in this case, it doesn't matter what initial condition we use. We switch to GFS initial condition, we pretty much get the same result. So hurricane intensity in this kind of presentation, in the global model context, 13 kilometers, we do not have the storm scale structure. So global model intensity has almost nothing to do with, little to do with the initial condition. It's really how the dynamical formula. So we get a much better improvement over either GFS or the IFS. So I want to look at this mesoscale resolving concept. Now we have to think about this. All the global operational models are already mesoscale resolving. Mesos beta, according to Isidoro or density distribution, is from 20 kilometers to 200 kilometers. So I loosely call it mesoscale. So in this scale, you should be able to, if you look at the kinetic energy spectrum, you should be able to see two slopes. One is the synoptic slope, the -3. The other is regarded as the mesoscale slope or turbulent slope, -5. And you want to see the transition. And clearly, every3 has captured this transition, and the mesoscale much better. ILS is basically just -3 all the way down to the free scale. And they have a spectral cutoff to delta X. And the GLS, for some reason, it loses the energy well before mesoscale. So quickly, going over time now, the Diamond Project is international. For the first time ever, there's an international comparison of global cloud resolving model. This is hard to imagine 10 years ago. But today, there are at least 10 centers in the world doing global cloud resolving simulation. So we have some very extensive comparison. I don't have time to go into this. I have to show this picture from the project. So again, this is called a Palmer cooling test, and compared to the best possible satellite, this is again the Himawari satellite. And I'd like to ask audience, there are 10 global cloud resolving models here. Can you pick one that's closest to the satellite? Which one is closest to the satellite? And this is two European ECMWF model, one French model, one German model, ICON, one Japanese ICON, Nikon, and two US model here, three US model here. Can you pick the right one? Any volunteer? Lower left. Yes, you chose it wisely. That's Indiana Jones thing. that's the NGGPS prototype. So you chose wisely. So quickly, I lose a lot of time. I want to skip this. This is really for Bob and the 40-day natural run using the 3 kilometer. I hope the next time I will show you guys 1 kilometer. I promise. Somehow, some way. But this is the 3 kilometer simulation. And thank you. I really apologize for taking too much time.
Thank you all for coming back. We're now going to head into the home stretch, and I just wanted to mention, I alluded to the fact that we had an additional guest able to join us today who wasn't on the original agenda. And so after we have our presentation from Rob Hoffman, we'll have Professor Milt Kalem before Dr. Benny Kurtman will give our last presentation of the afternoon, and then finally we'll get to hear from the guest of honor for a few minutes before we head over to the reception. And so at this moment, I'd like you to please welcome me and join me, Dr. Rob Hoffman. Thank you, Rob.
Thank you, good afternoon. Hi, everybody, and hi, everybody that's listening in on GoToMeeting. So I'm going to talk a little bit about OSSE's past, present, and future, but I'll also talk a little bit about my collaborations with Bob. And at the end, I have some photographs of Bob that I'd like to share with you. Most of those photographs were taken by Michiko Masutani, and I'd like to thank her for providing those photographs, mostly from lidar working group meetings. So this is a schematic of an OSSE, and I'll talk about the components of it in a minute. Yeah.
Press that window you're in.
Okay. So, like many of the speakers today, I'm going to start with Milt Kalem's group at Goddard Space Flight Center. That's where I first met Bob. I was in 1981. I became a postdoc for Eugenia, and Bob had already been a Fed for several years at that point.
What did you do?
What did I do?
Yeah.
Oh, I did this and that. So with Eugenia, I came with the idea of working on this ensemble forecasting that we called lagged average forecasting. And we had a fun with that paper, didn't we, Eugenia?
Yeah.
And then also I worked with scatterometer data, which is one of the key things that connected Bob and I in the next 25 or 30 years, I'd say. And today at lunch I met Mark Kane, who at the time I was getting ready to go to Goddard told me, if you could do something with that CSAT data, it would be great. NASA is looking for ways to utilize that. And he proved it was true. So as I said, Bob and I collaborated for a very long time on ocean surface winds. We were both on various NASA scatterometer teams. My most cited paper, and I think it's Bob's most cited paper also, is this paper in 2011 BAMS, which describes our CCMP for our cross-calibrated multi-platform ocean surface wind data set. And, you know, that's something that after I wrote my first couple of papers on using the variational analysis method to work with scatterometer data, I was ready to let it drop. But Bob encouraged me to keep going, and he provided some support to keep it going. And then we got on the scatterometer teams, and really it became a fairly big part of my career. So thanks, Bob.
It's been downloaded 2 million times.
Wow. But for the last 5 or so years, Bob and I have been collaborating on OSSEs. Since I retired, Bob convinced me to work on this, and I've been working on it part-time, and it's been very, very challenging, but really interesting research. And winds, you'll see, are a constant theme in the work and the collaborations between Bob and myself. Winds from satellites in particular, from scatterometers, from Doppler wind lidar, from the new Cygnus series of instruments. So now I'll actually talk about OSSEs, the topic of my talk. So they've been used for a long time, since the 50s, to evaluate observing systems, to guide decision makers, to allocate resources so that we can get the best bang for the buck, and to conduct trade studies of particular instrument designs. And also they can be used to design and test all sorts of methods. Eugenia gave one example today, but we can test both data simulation methods and diagnostic methods and model methods. So these are the components of an OSSE system. It starts with a nature run, and the nature run is basically a very long forecast from the best model you can afford, or that somebody else will do for you. And from that nature run, we can interpolate it to observation locations and simulate observations. And then those observations are used in the usual data simulation and forecast system, which should be close to an operational version if you can manage. But in the OSSE system, we know the truth. The nature run is the truth, so we can do calibration and validation versus the nature run. So this is an OSSE from the past. This is from the Charney, Hallam, and Jastrow 1969 paper, which was used for planning for GARP. And the two pictures I'm showing, which maybe are a little small, but I'll explain them. They show the RMS wind era at 400 millibars. This was a 2-level model. It had a 400 millibar level and 800 millibar level, and that was it. So we've come a long way, and it was also rather coarse. You can see I wrote down a 7x9 degree GIST model. And this is what we call an identical twin setup, where the model used to create the nature run and the model used to do the data simulation are the same. So in this case, they were interested, well, in the extratropics, we know there's a balance between mass and wind. So if we have good temperature data, we should be able to recover the wind field. And that's what you can see on the left-hand graph, where even with some noticeable errors in the temperatures, you can still recover the wind field. And these temperature errors range from perfect or 0 up to a 1 degree random error. But on the tropics, you really, even in this identical twin setup, you need to have exceedingly accurate temperature data to recover the wind field. And that's one reason why we've continuously been asking for better wind information. And that led over the years. Bob was involved with a lot of different lidar experiments and designing of lidar instruments, and was a PI on one that did not fly. But I'm going to show some results from some of these experiments, which compare two different technologies for Doppler wind lidar. One's called OWL, and the other we're referring to as a co-parent wind lidar. And at the bottom of the slide, I have some of the details for these experiments. So it's much advanced compared to what was done in the first experiment I showed in '69, but it's still rather coarse and simplistic compared to what we're doing today. But this one does include the hurricane nature run that was shown in one of the earlier talks. So this shows some typical results. And these are for winds in the tropics at 200 millibars. So these are the high-level winds at 200 millibars on the left and 850 on the right. And we have three curves, the control in black, the owl in red, and the coherent lidar in green. And the bottom shows the differences with respect to control along with some significance bars. So you can see that in general, the owl impacts are statistically significant. The coherent lidar also has a positive impact, but it's not statistically significant in this particular experiment. And this, from the same experiment, shows the simulation of the hurricane. So the the best track where the truth is the black line with the dots, and then we see the three experiments: the control in purple, the owl lidar in green, which does a little bit better than the others, and the coherent lidar here in red. So I should mention that there are different types of OSSEs, and depending on what kind of experiment, what the aim of your experiment is, you might choose one type or the other. So the ones that I've been talking about, the last one, for example, is what we call a full OSSE, where we have a global nature run that runs for quite a long time, and these are useful. These type of full OSSEs are expensive, but they're useful for demonstrating impacts in a realistic forecast and data simulation system. In some cases where you just want to try out a new potential type of sensor, it makes sense to start off in a cheaper setting. We call these quick OSSEs, and here we often take a single detailed forecast, the best forecast we can of a particular interesting case, a severe storm or hurricane, what have you, and we treat that as a nature run. And the same OSSE setup applies to quick OSSEs as well as full OSSEs. And it's good enough to show the potential of a new observation type. So currently there's quite a few OSSEs on the drawing board that are being done at the AOML and other places. We've got now 3 relatively new nature runs. We've been using the G5NR, that's the NASA nature run. It's a 7-kilometer, 72 level nature run. New global one is called ECHO 1280. It's 9-kilometer ECMWF operational model of about 2 years ago, and it has 137 levels. And then the basin scale nature run that was done at AOML, that's 2-kilometer, 61 levels. So all these are now available, and we've got a number of different NWP systems that we are using in these OSSEs, from 3D NVAR to 4D NVAR, and making use of the operational GFS, GSI, and HWRF systems. And I just listed a few of the observing systems that we're looking into now. And these include geostationary hyperspectral sounders, small sats of varying designs for infrared and microwave observations, the Cygnus data, which is now operational, so now we're running OSSEs, not OSSEs, Doppler wind lidar, and various aircraft systems. So now I'll talk a little bit about the future, and there's definitely challenges ahead. One big issue for OSSEs is having the right infrastructure in place so that we can do the experiments that are necessary. So OSSEs have to keep track of whatever advances are taking place in the operational system. So both the new data and new methods of doing data simulation and new models have to be paralleled in the OSSE system. And so that's going to require us to, extend and innovate in the future. And the thing right off the top of the list is, how can we afford to run these experiments? We basically need to be running things that are the same scale as operations. And it's not just a few forecasts. With the current mix of observation systems that we have in place, it's very hard for a new observation system to show any positive impact, or for that matter, any negative impact. There's just so much data going in already that the data simulation systems are relatively robust. So we can't just run 20 forecasts or 30 forecasts. We need to run months to show a statistically significant impact in some cases. Well, we can't afford to do that, so sometimes we're happy enough to show a positive impact and leave it at that. So looking ahead, I would expect to see much more realistic simulators in simulating the observations in OSSEs. One of the issues in using data in the real world is that there are biases or errors that are correlated. And it's difficult to, because we don't understand these in the real world, it's difficult to simulate them for our OSSEs. But we have to try and get a handle on that. And in the future, more and more forecast systems will be coupled systems. So we need to parallel that in our OSSE simulation. And not just the forecast model, but the data simulation systems will also be coupled. And we're seeing that in some operational centers now, or steps in that direction. And for sure, OSSEs can be applied in many different settings. And Bob has this long list of what he'd like to do, but again, resources are limited, but for sure it can be applied to severe storms, oceans. I see George in the audience, ecosystems, air quality, other components of the Earth system. So there's some things that anybody contemplating running an OSSE or anybody reviewing an OSSE should keep in mind now and in the future. So first thing, of course, is observations should be as realistic as possible in terms of coverage and accuracy. But you don't want to necessarily take the engineering model from the instrument supplier and simulate lots of observations, because those tend to be very expensive. And yes, they will give you more realistic errors, but they'll be small compared to other errors that we have to consider in data simulation. These are, for example, representativeness errors, which can swamp the instrument errors in some cases. That is the errors of what's left out in the model compared to reality. And I already talked about different types of OSSEs can be appropriate for different purposes. It's important to consider what your purpose is when designing an OSSE. And I think I pretty much mentioned a lot of this already, so let me go on to the next. So I learned from Bob that there are 4 critical questions that anybody doing an OSSE or reading about an OSSE should keep in mind. First, was the study completed, or can it be completed soon enough to actually be of use in guiding decisions? Second, what are the limitations of the OSSE systems? No OSSE system is perfect, and you have to keep in mind what the shortcuts that were taken are, what assumptions were made, and whether those invalidate how you're going to apply it. So you have to be careful about the limitations. And then there's 2 secondary issues that you have to be aware of. Is the difference between the nature run and the forecast model realistic enough? And are the simulated errors realistic enough? And this is really important because the data simulation system is going to balance forecast error and observation error in coming up with the analysis. And the analysis then is determined to a large extent by how well these are balanced. And if the errors are not realistic, it's not going to work out well. So thank you. I did it quick, but I have a few more memories, as I promised. I have a few photographs from past Doppler wind lidar meetings. So Bob's in both of these pictures. You can try to pick them out. And the bottom picture is easy because he's giving the presentation. In the top picture, he's in his usual position at the back of the room in case he has to escape. Oh yeah, and Bob wears a uniform. Other members of Bob's family are in the police force or other, so they have uniforms. Bob has his own uniform. So, as I said, these photos were by Michiko Masutani, and here's Bob staring at the camera at one of these meetings. But more often than not, he's paying attention. Here he is with a few buddies. Bob, maybe you can say who these are. I don't really know.
Chris Camerdi, Mel Shapiro, and Richard Somerville, who was the model developer of the GIS model in 1970.
Who's standing in the back?
Yeah, who is that guy? Self-identified. Here's Bob giving a presentation, and even scarier, here's Bob about to ask a question. So Bob, Welcome to your retirement. Okay, I saved some time for you.
You sure did. Thank you very much. I think following with the previous sessions, we'll go ahead and follow one speaker to the next, and we'll allow questions of the group as a whole. And so with that, I would like to invite Professor Milt Halem to the podium, who's visiting from the University of Maryland and also has a long career with Bob. Very long, I will let I myself was even unaware.
Well, first, I would like to thank Erica for getting me on this program today. Actually, it was yesterday evening that I asked her for a program, assuming that there were no regular scheduled talks. And then I see all my colleagues here on the talk, and I desperately requested some time. So she said she'll give me 10 minutes, she'll let me squeeze in, but she doesn't know me. I'm somewhat intimidated that I had to tell her that I have a talk of about 10 minutes, and so that's the title of the talk. It was changed a few minutes last night to introduce the word OSSE. I actually shortened LSTM, because everybody here knows what that is, right? Long, short-term memory. You're all using it. Everyone here is a machine learning expert. Well, that's where I've been these past 5 or 6 years. At the AGU Fall Conference, I was actually given a poster and sort of took some of these slides to make the poster. And on the other side, there's another row of boards, and there was this poster also talking about the butterfly effect, or Lorenz's 62 model, and it was Bo Shen. Bo Shen is a student of Bo Shen is a colleague, a staff person that worked with him at Goddard, and they did a lot of the model development. And so I ran into Bo, and I was planning to, I didn't have the title of his paper at the time, but he just sent it to me, so I even made an update to this presentation at lunch. So before going on with the formal talk, most of you do not attend, or I don't know how many of you ever attend, the supercomputing conference in November. This past November, the Gordon Bell Award, this is an award that's offered every year for the computation that was the most compute intensive ever up until that year. And that award went to a group at Lawrence Livermore National Lab and Oak Ridge National Lab for a paper they did called Exascale Deep Learning for Climate Analytics. And what they did was they took a 0.25 degree climate run for 100 years, and they developed what they call a type of convolutional neural net. They call it tiramisu. It has nothing to do with the cake, but they use that method to actually do automated analyses looking for extreme events over the 100-year run and letting the machine find it. Not just hurricanes, but you are all familiar with atmospheric rivers, right? Yeah. Now that brought me back to what we needed whenever we did forecast experiments. Just before I moved to Goddard, we had a scientist that was primarily a weather forecaster named Glenn Droyd. Well, he came from Israel and he went back to Bar-Ilan University, and we were in search of someone else to replace him. And we had this colleague, Jerry Spar, who was from NYU and was sort of working with us. And he brought us this young PhD student of his, Bob Atlas, and said he's done some numerical weather forecasting for the Air Force. He's pretty good. So we brought him on, not to do weather forecasting, but to do scatterometer tests for the upper layer thermocline. And he obtained his degree and then went back to Stony Brook on the island, where I had the duty to call him in whenever we needed someone to analyze a model run. Several years later, I'm going to show it. In 1977 or 8 is when the paper was published, we conducted some data systems tests in preparation for fvG, and we had run tens to hundreds of model forecasts. So we kept turning to Bob to look at the forecast to see whether we had any impact. And so it was in that paper that Bob developed what he called his AFM, his automatic rule-based forecast model, which he claims today is still the approach that he uses whenever he does his forecasting analysis. In the next chart, I took a photograph of that paper, and you can barely make it out. AFM forecast, I can't even read it. But anyway, he included in that paper, and I don't think anybody else has ever done it, something like 8 pages of flow diagrams for what a forecast analyst would do, first for dew point depression, then for vorticity exchange, then for temperature advection. And so every page in the publication in the Monthly Weather Review had another flow diagram that was Bob's rule-based approach. So now let me get back to the OSSE that I want to describe. But before I do that, I should point out that in doing OSSEs, which was actually named by the JOC, it's the UN Group Joint Operating Center, I don't know what it stands for, but they named these simulation studies as observing system simulation experiments, which Bob has carried on with for us over these many years. But what he did in one of the experiments that we were discussing, and I can't remember exactly why we wanted such a precise example of the nature run, it was his suggestion that we even use the nature run to simulate the RAOBs and the RAWINSONs and all the other data that we use to do the data assimilation. And I hope you still remember all the work that you did in creating an OSSE that actually used the nature run to create the whole classical observing system. But today, I'm going to show you an observing system that is based on the Lorentz 63 model that uses as the nature run a Runge-Kutta high-order scheme to solve the system of 3 ordinary differential equations. I'll show it to you in the next slide. And then for the experiment, we will assume that we have a model, and we use essentially the same Runge-Kutta scheme, but we take larger time steps. We add noise to each of the 3 equations. And as Ross says, well, is that a real deviation from the nature run. But anyway, that's what we took. We made ensemble predictions at every time step to simulate the ensemble common filter that Dr. Kalme is responsible for. And then we validated these results versus the model. So here is one of the simplest set of equations, just three ordinary differential equations, but they're coupled and they're nonlinear because you see in two of the equations an x times z and an x times y. And so we have three unknowns, x, y, and z in these equations. And if you attended the centennial honoring the 100th birthday of Ed Lorenz and Jules Chani, you would have heard the story about how his secretary copied down the final solution one night before going home that was running, and then the next day when they tried to reproduce, to continue the integration, there were some slight differences in the initial conditions, and that led to the so-called butterfly effect. And because of time, I'm not going to show the beautiful movie that's captured in this last image here of the wings of a butterfly from that particular set of initial conditions. And so the differences in the two initial conditions is x is 3.014 and the other one is 3.013. So we're really down to the fourth significant digit in these differences, and they give rise to different plots. We implemented, I just want to make sure here. So we implemented a neural network which has memory. And the memory is that it can recall what the effects of the influence of the neural network was from previous time steps, and you could set parameters going back somewhat in time. We used, to compare the standard methods for doing our common filter, there's a group at NCAR that has developed a package called DART, which has a whole set of different data assimilation schemes. And so we use the DART ensemble common filter on classical computers. I should point out that the experiments I'm going to describe are run on what is called a GPU. It's on a two-node system consisting of each node having 4 GPUs, and we use them as to do the neural net computations. But LSTM is a very complicated neural net. Most neural nets are essentially an input to a neural cell. The neural cell collects the inputs from all the other sources. Every input has a weight. It does the weighted average of all the components, and then there's an activation function which sends it off to another cell. This neuron has all these other gates embedded in it. And so if we look at the chart, which has, I guess I could point to it. If we look at this input, it sends a value here, and there's a weight that's assigned to this term. But at the same time, the value h is brought along from a previous time step, and there may have been several previous time steps. And those two values are fed into what is a neuron or a gate. So it's a neuron within a neuron, and it sort of sums these two weighted with their values. And then there's an activation function, And that activation function then sends it to this value. And it's called, this node gate here, it's called the forget-me gate. In other words, if it doesn't want to put much weight on the path, it'll give it a 0 weight going forward. If it wants to put some weight on it, it'll add a little bit, and that gets carried along here. And then you feed it another value, and it comes back to this gate. And so there's a series of values that's characterized and memorized up on top, and a series of values that's memorized on the bottom. And there's all the gate influences, and then there's an output, and then there's a place where the H and the C go for input to the next memory. So this is the kind of neural net, a very complex one that was developed somewhere around 2010 by someone you probably never heard of, from McGill. And so we ran this neural system as our for doing our neural net-based ensemble Kalman filter calculation. And since this is really a meeting to honor, to recognize the work of Bob Atlas, I don't want to spend too much time on it, but in any event, here is the way the system works, all the concatenation states, so this is the generation of the various data sets where where it shows the noise that we've introduced into the solution. And I'll skip some of the data that I'm doing the 96 resolution model, but this is what I want to show basically. So just like any data assimilation, we start off at this point. We integrate along, so our model, even with the noise, is following the true solution, which is blue. We stop the insertion of data at this point. The solution continues, but by here, they begin to depart from the true solution. The true solution goes around here. I think we're on the blue line. We go around here. And at this point, we start to insert data again. And so we jump from here to there to there. And by a few time steps, with this ensemble common filter, we're back in adjustment on these two wings of this butterfly. So this demonstrates the effectiveness of this approach, which is where things are, in a sense, going in the future. People now have been using neural nets to train and actually generate cloud resolving parameterizations that replace the actual physics. So we're now able to do with neural nets physical parameterizations, which you can instantly calculate without having to run through a series of physical calculations. Also, we're beginning to recognize that with GPUs, we can really improve the performance of actual finite calculations, and that may well be where the future of computing is going over the next 5 years, where we expect to see 2 orders of magnitude in computer generation still following Moore's law till at least 2023. So one second. So I think I may have finished quickly, which is what I want to do, but I also want to conclude with my remarks that that event dating back probably 45 years, when Jerry Spar brought Bob to my office in New York, that has been both for me and I guess led Bob, because he decided to stay with me when we moved to Goddard, rather than take some other position that was offered to him, and then went on to his NOAA career and to his contribution to the whole field of meteorology. So Bob, I'm extremely fortunate in life to have encountered you. Bye.
Wow, thank you so very much, Milt. I really appreciate you making that work and for being able to have you here today. We're going to transition into our last presentation for the afternoon, and we are going to have your host, Director of the Cooperative Institute for Marine and Atmospheric Studies here at the University of Miami, Dr. Ben Kurtman. And I may not be in the room, but when Ben finishes, so Ben, you'll transition over to Bob.
Sure.
Oh, and Gopal wanted to, I think, thank the speakers. So we all have fun figuring that out.
We'll figure that out.
Thank you very much, Ben.
Yep. So, Bob, thanks so much. I'm happy to be here. Happy to give you a few of my impressions from when I met Bob. I was a graduate student, had just switched over from applied math to meteorology, and I was still at that stage where I felt that all these meteorologists were just making things up. I mean, this idea of potential temperature. I mean, it's either temperature or not. It doesn't have the potential to be temperature. So I was really at that stage. And Bob, it's hard to find pictures of you out on the internet. I was really trying to get some photos of you when you were a lot younger. I think I found one from about the time when I took a class with Bob, which was the previous century, back in 1989, which is an important year, Lou, and that's going to come up at the end. Yeah. And the little inset there says Oxnard. You can't quite see it because the go-to-meeting stuff. It's kind of a small world funny story. This is, I think, August or July, something like that. I'm in a gym in Oxnard, California. I have family out there. My wife has family out there, and I'm working out in the gym. And this guy comes in a white shirt and shorts, and he looks an awful lot like Bob Atlas. And I'm squinting, and I'm trying to run on the treadmill, and so I start waving my arms because it's Bob Atlas. I'm trying to get his attention, trying to wave in the mirror. I'm waving. I can never get his attention. He does his workout late, and I didn't. I was having one of those rare runs where it was actually enjoyable, so I didn't get off. And then I sent Bob an email, and it turns out that Bob is planning on spending a fair amount of time in Oxnard. I spend a fair amount of time in there because of family, and so we have a place to collaborate in the future. Small world story. Anyways, so I just want to go in reverse order from some of my own personal experiences, Bob, and to comment a little bit how Bob's work and influence has influenced my own work. Perhaps a little less quantitative than some of the previous speakers, a little more briefy, but nonetheless. So the first one, of course, is the collaboration with Siemens. So as you can all imagine, as the director of the Cooperative Institute, I have to have a collaboration with Bob as the director of AOML, and that's worked just beautifully. I have just nothing but positive experiences from working with Bob. And one of the things that I want to emphasize, and this is a paper that Bob and some colleagues at AOML and here at Rasmus, and it's been discussed before, that won the AMS Banner Miller Award, really quite impressive. But there's an important part of this paper when you look at the authorship that it actually points to. One, that Bob is really actively collaborating with the faculty here. And Lisa Bucci, who's in the audience, she's like the poster child for what I think Bob's vision of what the Cooperative Institute really brings to bear. So Lisa's an employee of the Cooperative Institute doing science. At the same time, she's getting a PhD here at Rosenstiel and has just given me her letter of resignation. Thank you, Lisa, because she is transitioning to a federal workforce position as of March 1st, I believe it is. So from my perspective, that's really Bob's influence, that he recognizes that through the Cooperative Institute, through students, this is the way we grow the next generation of scientists that are going to shape how the field evolves. And I'm really, really impressed with Bob's vision in that regard. The other thing, also in terms of Bob's vision, is that he recognizes that the CMS employees need to have a career trajectory that they can establish their own independence. And that's not always true in the Cooperative Institutes. And so Bob has set a culture at AOML for the CMS employees that they can actually develop their own career trajectories. They can write proposals. They can be leaders in the field, recognized for their own contributions. And that's really important. It helps them establish a career and really have a long-term future in this field, and helps me retain them as employees. So I just wanted to comment on that. The next, in reverse chronological order in comments here, Bob may not remember this, but he actually had an influence on the North American Multi-Model Ensemble. This is a project that's very, very near and dear to my heart. It's a project that I developed in collaboration with many, many colleagues over many, many years now. It's now an official NOAA operational product, but we were at this very delicate moment in time when we were asking NOAA to treat this product that has, operational centers involved, but also, goofy guys like me involved. And we're saying, will you be willing to treat this as an operational product? And Bob said, yeah, I'll start talking to people. I'll go to bat for you. And he went to bat for us. And he talked it up, NOAA management, and NMME as of 2016 is now an official operational product. And so, Bob, I am most grateful for that support. So this is just the web page for the NMME. And just in case you guys wanted to know, here's the seasonal forecast for the next 3 months in probabilistic format. Looking pretty warm everywhere. By the way, the SSE forecast looks like that almost every single time. It's been kind of warm in the ocean lately. But the forecast for March, April, May is a little bit wet for here in Florida. Not surprising. And then that's the forecast plume from the NMME project. So I'm sure Bob would be proud of all those ensemble members contributing. Boy, you get out to September, you don't have a whole lot of confidence in any one forecast, do you?
Sometimes it's amazing how sometimes they do converge. Really cool.
They do. It's true. Sometimes they do.
It just shows the ring up.
There's a lot of work to be done. Yes, Louis. Yes, Louis. There's a lot of work to be done.
Yeah. I'm saying is that this period has been the least predictable, even in the short range.
Yeah, that's true.
For years. I mean, you got to go back years before you see a domain.
That's right, and we don't know if that's climate shift or what's really do that. Now we've heard finally got a little bit younger picture in there, Bob. We've heard a lot from Bob about in all these presentations how much Bob has influenced high resolution modeling. So when I was first started out working with Shukla at Kola, he asked me to develop a prediction system, and so I just started making forecasts, and we were really excited about this. And Shukla sent me to this conference at the Oceanography Society. I don't know if anybody has gone to these meetings, but they're very expensive. The Oceanography Society really does it up. Anyways, this was in Hawaii. I don't know if Bob remembers this, but he and Ross Hoffman were doing all of this work with the scatterometer data, very high resolution work with scatterometer data, and I gave my talk, and I'd already had Bob in class, so I was familiar with him and saw his presentation, and he came up to me afterwards and started really chatting up the notion of resolution, really making the case of why that scatterometer data was so important, because there were airspeed feedbacks that we were, at the resolutions we were running in those days was, you know, we joke about 500 kilometers, and a couple of models we were using was about that, maybe 250 kilometers. It was pretty low resolution. And so Bob was just really sort of trying to plant a seed. And I remember that to that day. And, you know, there's another just reference to some of Bob's work. This is the paper I actually referred to in some recent work that we did. This is showing, in part, Bob's influence. These are multi-century climate simulations with, on one side, the typical IPCC class climate model. This is showing you surface current speed from the two models, and then this is showing you a global coupled model. The global coupled model at a tenth of a degree in the ocean and coupled to an atmosphere at 50 kilometers. So really showing you that we're starting to get very, very close to models that actually look like the planet Earth. And another influence, this will come back to class, when I took a class from Bob, but Bob really did a lot of nice work arguing that when you think about individual storms, that the air sea feedbacks are important for the development of individual storms. And this came up in class. And this is just from those two long coupled simulations. This is just looking very locally at air sea feedback and just sort of one-dimensionally asking how do the atmosphere and the ocean talk to each other. And so if it's bright red in a very hand-wavy way, it's arguing that the ocean is primarily driving the atmosphere. And if it's blue, it's making the argument that the atmosphere is primarily driving the ocean. And so what you can see at high resolution, you completely different structure of who's talking to who's forcing who, and compared to the low resolution model over there. And what I want to ultimately argue is even on longer timescales, beyond synoptic timescales, that makes a big difference on storms. And so here we're actually arguing that we can predict 2 to 3 years in advance. This is a predictability study. 2 to 3 years in advance that there's going to be an increase in snowfall in the mid-Atlantic region. That's the increase in snowfall in percent. So it's just a few percent, 1.5%, 2%, but averaged over a 2 to 3 year period. And then this is showing you the probability of exceeding. The climatology is in gray, and the cases that are tied to undulations in the Gulf Stream are in blue, and showing you that we're increasing the probability of extreme snowfall in the Northeast, evaluated over a 2 to 3 year period. And so these are things that come in these high resolution models. But I tried to do the same thing in that low resolution model. There would be no signal whatsoever. And so I want to acknowledge that this, and Bob's not the only one, it's a number of people really making the argument, if you want a credible climate simulation, you want to actually capture the phenomenon that people care about, you really need to start thinking about resolving that phenomenon. So I think that's a really important legacy that Bob's left with us. Finally, in the classroom, I want to talk, and this gets back to Lou. So this was in 1989, Lou, and so by the way, so one of the textbooks that Bob gave was from 1960. So, okay, so here I am, a graduate student, just switched from mathematics to meteorology, and I'm told that the textbook is a NALAC manual, however you say that, from 1960, right? So I said, oh my goodness, what am I in for, right? But it turned out it was a wonderful class. It was a great class. I learned a lot about synoptic meteorology, and I also learned a lot about the 1979 President's Day storm, because this was fresh. This was 1989. Bob and Lou were clearly, because Lou's name came up a number of times in this class, were clearly actively debating this storm. And I had never met Lou. I'd never seen him. I didn't know who he was. All I knew is that Lou had left NASA and gone over to the dark side. That's all I knew. So, and it was a great class. In fact, Bob, I don't teach synoptic meteorology. No one would ever trust me to do that. But I do teach every once in a while a class in thermodynamics. So I do talk about potential temperature. And I do visual aid, I do try to teach them the QT diagram, because I actually get a big kick out of the QT. And this is circa 1989 from you. This was given to the whole class, so it's not a unique gift. But you can see it survived since 1989. I show it in class when I teach atmospheric thermodynamics, and it says U.S. Air Force or USAF QT log P diagram. So, Bob, thank you for this QT. My students appreciate it. So I will end there. Bob, I'm looking forward to seeing you in Oxnard. Hopefully we can hook up in someplace other than the gym. And those are my impressions of Bob since I was a graduate student. So Bob, thank you.
Thank you, Ben. And when we got together to organize this, because we're going to run long. Bob, you're the only one left who could put a wrench in it. But I know you won't. Since we are a little bit early, we do have a moment if there are any questions. I think Ben might have, okay, Ben's leaving. So other than Ben, so the other two speakers, if there are any questions from the previous two presentations. Oh, and Ben's back. So we had Ross and we had Mills. Yes.
Yeah.
Oh, let me get the microphone.
Ross's presentation, slide 14.
Oh my God.
Okay, can you find that for us?
Part of the transparency, that's right, he would erase the.
Oh yeah, that reminds me of a memory of Bob. When he would come to meetings, his talk wasn't prepared usually ahead of time. He would come on the airplane with a stack of transparencies about this thick, and then he'd sort them out and whittle them down to the requisite number.
Was it 14 or 15, Louis?
No, it's 14.
Okay.
So the thing I want to take note of, because now I just want to speak from the receiving end of a manager in management that has to make decisions based on either OSSEs with two S's or an OSSE with one S. And I took note of Bob's comment that from the European Senate perspective, he sold it on one case. Right?
Yes.
You mentioned
Yes.
the one case. So you talk about, everybody, from a science perspective, everybody wants the statistical significance of an observing system, so you run it for a lot of cases. But I'm telling you that more often than not, it's the second one that makes, and the reason is when you do the statistical analysis, you get a difference, like about that much, maybe even, you see any space between the fingers, just a little bit of space. And the reaction, I remember James Baker on one of these saying, you mean you want me to spend $1 billion on something that's different? I got to go to the Hill and sell $1 billion observing system, you got that much. But if you show one case, and it's a dramatic example, you're gold. Just think.
Well, that's true, but when you are looking at that one case, if you can't explain it physically, you have to actually look at what synoptically is going on to support your
I'm looking at the
argument.
hurricane program that sold in about 15 minutes after all that science work. You've got, it's like a gong show, folks. I'm just letting you know. And if you don't catch them in the first 5 minutes with something like this, and the same thing was happening even with the two satellite systems versus the one, where we had 2 out of the 7 cases that had made differences for the East Coast. We made sure that was very clear. Those individual cases, and if you think I get a little bit of edge, it's true because I was just criticizing for looking at one case for so long. But it is, I just noted on your chart here, you did point to a single case, and there were more decisions made that way than the other one. Just pointing that out.
Thanks. Well, I got something to say to Milt. There was a lot of talk today about things that went on in Milt's office, and I greatly appreciate being invited to those regular staff meetings in Milt's office. I was just a postdoc. So thank you. And, you know, out of Milt's group, we have Eugenia and Bob and Shukla, 3 great scientists who became great leaders. And I wanted to ask Milt, is this because you're such a good mentor, or do you know how to choose them right?
Probably a little bit of both.
There were a number of people that we brought into our group who were turned down for permanent positions at MIT, and others who were postdocs that had very difficult times being accepted, that subsequently spent time with us and then went on to become leaders in the field. I'll actually cite the name. Dave Randall, for one. Fung, and that Fung is the woman I was just referring to in the National Academy of Sciences. Max Juarez, it was another one all these years. So they weren't all coming as superstars. Shukla took a lot of negotiating with, but I had someone like Johnny to twist his arm, and Max, I had Arakawa to twist his arm, and then there were some people that joined us and went on to other careers, like Jerry Herman, and I had to twist on Johnson and or someone else there to allow him to come. So you can't predict who's going to be a superstar.
So at those meetings, you know, we talked about the science and the specifics and the details, but we also, you know, Milt was always coming back to how we presented what's important, what's really relevant. And, you know, those were lessons that kind of went by me, but the others took them on.
Yeah. Anyway, while you're getting all the praise, let me just say that Milt will come to me sometimes. So I have this question. What is your opinion? I want to hear your opinion. I said, Milt, this is what you should do. No, absolutely not.
Okay, thank you very much. I think we'll all wanted to recognize everybody before we move on to have Bob close the day.
I would like to thank all the speakers, one for the patience, in the sense we got it moved a couple of times, and still all of them, the group that we are talking about, they were able to come back, same group that we had envisioned from the beginning. I really thank you all, each one of you all, for coming here, taking the time off, and then giving nice things that talks and nice wishes that we could it maybe go back 20 years to think what Bob would have been 20 years back, how good he was. And thanks to everyone. With that, I would let Bob take.
Thanks. I'm not going to give a long speech now. I imagine that I'll be giving a speech in the reception, and I don't want to say the same things twice. But I do want to say, Gopal beat me to it, but I want to say a thank you to every one of you who came here today, and also especially for each of the speakers. And many of the speakers traveled big distances to get to our not the greatest weather. No, this is great weather here in general. I did want to say that for this special occasion, I wore my Hawaii shirt, but we used too much bleach in the wash, so it's white today. Louis Cellini, who started this off with his great talk, I was very lucky to have Louis and share an office with me. I think we both benefited from it immensely. I know that I learned a lot from Louis on things that I didn't get in my education up to that point with regard to mesoscale meteorology. And perhaps the biggest thing I learned from Louis was the coupling of upper and lower level jet streams, which I believe was your PhD thesis. When I think it's important, whether you're a teacher or a scientist, to always have an open mind. When I heard this, it immediately struck me as this makes perfect sense. This is correct. His arguments in his papers were convincing, so I incorporated it into the classes I was teaching at the University of Maryland. And many of the students who took those courses ended up in the Weather Service, some in high positions like Tom Cuff, who was the head of the Ocean Prediction Center and now is in charge of their observations portfolio. So Louis, I think it was beneficial for both of us that we shared the office. I think everyone has some idea of where I came from. This might have been a good thing to do when I first arrived in Miami. But Milt Halem had a very big influence on the way I handle myself as a leader, and so did Yehenia Kalme, who were both my supervisors at early times in my career. And I'll say one of the things that I learned from Milt was the importance of having an open organization, one without walls. And when I worked with Milt as a brand new PhD scientist, I got to work with some of the best people in the field: Ed Lorenz, Jules Charney, Norm Phillips, Akio Arakawa, Yale Mintz, incredible people for a young PhD to be interacting with, and also Don Johnson, who was Louis' professor. And I like Don so much, I'm not sure if I adopted him as my mentor or if he adopted me as another student, but I learned a lot from Don as well. I think it's important throughout our entire lives to be learning. And one of my goals when I retire is to learn things that I've been wanting to learn and I haven't had time for as a research scientist or as a director. Now I have time to do a little more reading. I have time to explore certain aspects of the field that I perhaps maybe am not in the applied research area, but one of them relates to what Bowen has been working on, Bowen Shen, which is chaos. And I believe that there's a lot of things that we consider chaotic in the atmosphere that we just don't know the order yet. We haven't learned it yet. And so I hope in my retirement to find some of that order that we don't know yet. So that's probably basic research, but things that would relate to prediction down the road. Let me see, my interactions with Shukla over the years, always great. I was very stimulated by his desire to really determine, can we predict at longer time scales? And I think with Ben Kirkman's work, we're seeing some real skill in that area. S.J. Lin, I can't say enough about S.J. I consider him the best modeler we have in the nation today. I had the pleasure of being his boss when I headed the NASA Data Assimilation Office. Everything that S.J. ever said he would do, he did, and he did it generally in less time than any of us imagined it could be done. Let me see, who am I missing? But Frank Marks was my first friend here in Miami that I would come down to visit because he got involved a little with Doppler and lidar. And it was on one of these visits to Frank and to my son and my granddaughter in the Keys that Christina Katsaros came to me and lobbied me to apply for the position as AOML director. And and then finally, Ross Hoffman, who has been one of my best colleagues. We've written many papers together and done work that's continued into his retirement. Maybe some things will continue into mine as well. But I'm very grateful for all of you who came here today, for all of you who are watching online. And I can't, I will say again in the next room when we do the reception, but it's been an incredible privilege to lead the Atlantic Oceanographic and Meteorological Laboratory. The people working there are absolutely fantastic. I think we've made tremendous progress, and everything that I heard my first day at AUML, I think we've accomplished. The things that I was asked to try to do for the laboratory. So great people, and I'll see you all in the reception.